In this video, we're going to introduce the idea of linear programming in two dimensions, in other words, with two variables. So linear programming is a process that helps with decision making when an objective, or we can think of an objective as a goal, depends on multiple variables. So essentially think of it as an optimization problem. We have some variables in the problem. We're trying to determine the combination of values those variables would take on in order to optimize a situation. In other words, in order to maximize something like revenue, sales, profit, something like that, something we want to be high, or to minimize something, maybe something like cost, something we want to be low. We're trying to determine what combination of values could those variables take on so that they meet the requirement we want. In other words, they minimize or maximize based on the goal we have, while staying within the limitations we have. So keep in mind, in real life, scarcity automatically is a big issue. We have limited resources in order to accomplish any goal we want. We only have so many hours in a day. We only have so much money. Those kind of things are always limited. What we're trying to do is we're trying to optimize how we apply our resources in order to essentially create the best outcomes, maximize what we want to maximize, minimize what we want to minimize. So the easiest way to explain how these problems work, how all the parts fit together, is just to look at an example. So we're going to look at an example. We're going to break this down, go step by step, look at all the different components of this problem, talk about how they fit together, and then we'll talk about how we'd actually solve a problem that looks like this. So in this section, we're going to look at one way of solving called the geometric approach. What we know about linear inequalities, graphing linear inequalities, graphing systems of linear inequalities, we're going to use that in this particular section. Okay, so here's the setup. It's pretty long. We're going to break it down step by step. We're going to organize everything, and then we're going to delve deeper into it. Okay, so a tent manufacturer makes a standard model and an upgraded expedition model. Okay, so we've got two different types of things being manufactured, a standard tent and upgraded tent. Each standard tent requires 1 labor hour in the cutting department and 3 labor hours in the assembly department. Each expedition tent, the upgraded model, requires 2 labor hours in the cutting department and 4 labor hours in the assembly department. The maximum labor hours available per day in the cutting and assembly departments are 32 and 84, respectively. The company makes $50 of profit on each standard tent and $80 of profit on each expedition tent. So our question is, how many tents of each type should be manufactured each day to maximize the company's profit, assuming that all tents are sold? So in other words, think make to order. We're going to make everything and then immediately turn around and sell it. So before I do anything else, I want to organize all the information I have in this problem. I can think of things being broken down into 4 categories. So we have a standard tent versus an upgraded expedition tent. And then based on each of those, we have time in the cutting department and time in the assembly department. So that essentially gives us a way to categorize in 4 different ways. Does it fall under standard tent or expedition tent? Does it fall under cutting department? Does it fall under assembly department? Okay. So in my first column, I'm going to organize everything I know about creating a standard tent. So first row is going to be what happens in the cutting department. Second row is going to be what happens in the assembly department. So for a standard tent, we have 1 hour in cutting and 3 hours in assembly. For an expedition tent, the upgraded model takes a little bit longer to make. So we have 2 hours in the cutting department. We have 4 hours in the assembly department. And then by department, notice I have some totals that I can't pass. So it says that we have 32 hours to allot for cutting, 84 hours to allot for assembly. So however many hours I use, I can't use any more than 32 for cutting. However many hours I use for assembly, I can't use any more than 84 because those are our limitations. That's as high as it can go. Now we also care about what are we going to make on each of these. So for each standard tent we make and sell, we're going to make $50 of profit. For each expedition tent we make and sell, we're going to make $80 of profit. So if you go through the problem and categorize all the information you have, that organizes everything. Now, how do you know how to go about organizing something like this? I want you to identify things that represent totals. So the totals we have here are the 32 and the 84. Typically, we want to arrange the rows based on how numbers relate to a total. So the first row relates to cutting. The first total we have in the problem is the total number of hours available for cutting. So the way I organized it is by standard tent and expedition tent, as those are contributed in the cutting department. And then same thing for the assembly department. That's the other total I have. So I want it organized by tent type in that particular department where I have a maximum number of hours of 84 that are available. And then our profit, notice I've kind of separated that out. These are our resources. Think of these as the resources we have available. This is how much we need. This is how much available for each of these two departments. This information contributes toward what we're going to call our objective, the goal. So the question at the very end was how many tents of each type should be manufactured each day in order to maximize. There's the key word. The objective is maximizing. Well, maximizing what? We want to maximize profit. Well, this is the amount of profit we make per type of tent. Our goal is to optimize the situation so that we're combining these amounts together and getting the most profit we can while still observing the fact that we're kind of limited as to how much time we can spend doing anything. So our goal, the objective in this case, is to maximize profit, which is what we're going to call P. Based on this goal, we have what we call decision variables. We're making a decision in terms of how to allot our time. How much time are we going to spend doing one activity? How much time are we going to spend doing another activity? These variables are the ones we're trying to find values for. So remember, the question was, how many tents should we manufacture? Well, we have two different tents we can manufacture. Depending on how many of those we make and sell, that contributes a certain amount to the profit. So these are the values we're having to decide on. We're having to decide how many standard tents to make, how many expedition tents to make. So we're going to call X the number of standard tents. We're going to call Y the number of expedition tents. Those are the decision variables in this problem because we're deciding what values those variables are going to take on in order to optimize this situation. So based on our goal and our decision variables, we have what we call the objective function. This is going to be the actual relationship we want to maximize. So all these times we've talked about sales, we've talked about revenue. If we take how much we make per tent, multiply it by the number of those types of tents, add those together, then we have the two components that contribute towards our profit. So the total profit is going to be $50 times how many standard tents we make. That's the portion from sales of standard tents. $80 times the number of expedition tents we make, so 80 times Y. Each of those individual components contributes to our profit as a whole. So we add those together, and when we add those together, that totals out to our total profit. This is the objective function because it's related to the objective. The objective was to maximize profit. Well, this is the function, this is the relationship that represents profit. So the ultimate goal is to determine what values of X and Y we want to choose so that this total is as high as we can get it, while again still observing the fact that we can't just spend indefinite number of hours in cutting and indefinite number of hours in assembly. So this is called our objective function. We want to maximize that function. So the goal is to find the optimal value, in this case, the maximum value of that objective function based on the different ways we can assign values to our decision variables. There are different numbers of tents we can make of each type depending on how much it takes to make each and what our limitations are. We want to find the combo that's going to give us the best outcome. In other words, it's going to stay within the limits we have, but it's going to give us the most profit overall. So now we need to determine how are we limited. If we just made as many tents as we want, then our profit could be infinitely large. If we could make 100 tents of each type, we'd make money. If we made 1,000 tents of each type, we'd make more money. We know we can't do that though because we're limited. So we're going to write problem constraints, in other words, inequalities, to represent the limitations we have as far as our resources are concerned. The way we write these, again, is going to come back to the totals we have. So the totals we had information about were the totals for the cutting department, the totals for the assembly department in terms of how many hours we can spend in each of those two departments. So the standard tent takes 1 hour to cut, the expedition takes 2 hours of cut. So say we made 5 standard tents, well, that would take us 5 hours in total. Say we made 5 expedition tents, well, that would take us 10 hours in total. We know that by combining those two activities, we have to stay within that limit of 32. So if we multiply the number of hours it takes in that department for each of our types of tents, multiply each of those, how many standard tents we make, multiplied by the 1 hour, how many expedition tents we make, multiplied by the 2 hours, add those together, those two contribute towards the total. We know that that total has to be less than or equal to 32 because 32 is the maximum number of hours we can spend cutting tents. Now, same thing for assembly. A standard tent takes 3 hours to assemble. An upgraded expedition tent takes 4 hours to assemble. So 3 times the number of standard tents we make, that's that portion of the total. 4 times the number of expedition tents we make, that's that portion of the total. When we add the amount of time spent on each of those different types within that department, we know it can't pass 84. It can go up to 84, but it can't pass it because 84 is the maximum amount we have available in terms of time in that department. So those are going to be the two problem constraints. Those are going to represent how our resources are limited. It's going to tell us where can we max out. So the goal is to find the highest number of profit, the highest amount of profit we can get, picking X and Y to maximize our profit, while X and Y still fit within these inequality constraints. Now, because this is a real world situation, like we looked at last section, we also have some non-negative constraints. Since X and Y represent a number of tents, we can't have a negative number of tents. So we can make 0 tents, that's a possibility, but we can't make -1 tents. Now, technically speaking, we would also have to have integer solutions as well. We can make 1 tent, we can make 2 tents, but we can't make 1.5 tents. We'll have to just interpret that ourselves once we start to look at the numbers, once we actually get into some of the algebra, some of the graphing. But just keep that in mind. We do have some constraints additional in this situation just based on the fact that we're looking at a real world problem and things that can't be negative, things that can't be fractional. Okay, so put it all together. What do we have so far? We can generate a mathematical model, what we're going to call a linear programming problem, by putting all of these things together. So our goal is to maximize our profit. Well, this was our profit function. This is our objective function. The objective is to maximize this function. In other words, find the highest value that P could take on based on the values we choose for X and Y. Subject to, in other words, limited by these particular inequality relationships. So remember, this was the inequality for cutting, 1 hour for the smaller tent, 2 hours for the larger tent. We have 32 max that we can spend in cutting. And then this is the assembly constraint. So 3 hours for the smaller tent, 4 hours for the larger tent. We have 84 in total that we can allot. So whatever values we choose for X and Y, we want them to make our profit as high as it can be, but the values we choose for X and Y still have to fit within those inequalities. And then again, we have our non-negative constraints. Notice I've written it as one inequality there. I just put X comma Y greater than or equal to 0. That's just saying both X and Y are greater than or equal to 0. So you can write it as 2 inequalities, or you can write it as 1 that way. So what we have now, we have our linear programming problem. We're maximizing this function subject to these constraints. I'm going to forget about the function for just a minute, and I just want to look at the inequalities. What we now have is a system of linear inequalities. We talked about how to solve something like that. For the moment, we're going to forget about the objective function, and we're just going to solve that system of linear inequalities by graphing. So we're going to graph that set of linear inequalities, and it's going to give us a feasible region, a solution region for possible production schedules. Well, what does that mean? possible ways we could assign values to X and values to Y. Remember, in the context of this problem, that means the hours spent on a particular tent, or the number of tents made, and then the number of tents of another type made. So I have to graph these two linear inequalities. Remember, I'm going to convert them to equations for a minute. That's going to give me the boundary line to graph. I'm going to pick a test point on one side of the boundary line, plug it into the inequality, and verify whether or not it makes the inequality true. If it makes the inequality true, I shade the side with that point. If it makes the inequality false, I shade the other side, the side that doesn't contain that point. So we're going to do that for these two inequalities. This is going to be the graph we come up with. Now notice when I graph this, I didn't count by ones. That's because our numbers are a little bit larger. So if we have to get all the way up to 32 or 84, counting by ones is not going to be that great of an option. So in this case, I counted by fours. I ended up with intercepts at 16 and 32 for one of my boundary lines, at 20 and 28 for another one on my boundary lines. Actually, that's not 20. I think that's like 21, 22. Okay. Anyway, though, so we're looking now at our corner points that define our solution region. We have our shaded region. Notice that it's confined to the first quadrant. Remember, that's because of those non-negative constraints. So I graph the boundary lines, I shade. I'm looking for where the shaded regions overlap. So what we know is that any point in this region represents a possible solution to this system of inequalities, these problem constraints. What we're looking for, though, is the best option, the best solution. There is a best solution. What does that mean? We call it the optimal solution. The optimal solution is going to be the combo we want. Because remember, the goal was to find the combination for X and Y that makes our profit as high as it can be. So it needs to be something that satisfies these inequalities. Well, anything in this shaded region satisfies the inequalities. But we want the combination that not only satisfies these inequalities, but also gives us the highest profit that we can anticipate based on the two values for X and Y. As it turns out, the optimal solution, the combination that we want, the best option, the one that's going to maximize our profit, is always going to occur at a corner point. So remember, corner points, those are the locations where our boundary lines intersect. In this case, the region we have has 4 corner points. We have one at the origin, we have one at 0, 16, we have one at 26, and we have one at 28, 0. We have 4 corner points. One of these combinations, think of these each as an ordered pair with a possible X, a possible Y. One of these 4 combinations is going to represent the optimal combination of X and Y such that our profit is maximized. So what we're going to do then is we're going to take those corner points that we've defined for that region and we're going to write them down in a table. We're going to use a table with those values of X and Y to find the value of the objective function, the thing we want to maximize, determine what does that come out to. What's the actual value for P based on that chosen value for X and Y. The chosen values for X and Y are the values that come from those corner points. What we're looking for is what combination of X and Y at those corner points gives us the highest number for P. Okay, so let's take that and put it into a table. So our corner points again were 0, 0, 0, 16, 28, 0, and 26. My profit function was 50x plus 80y. So my goal is to find the combination of these values that makes P as large as it can be. So I'm going to take each of these combinations and I'm going to plug them into my profit function, which will tell us what the profit would be if that's how many items we make. Because remember, X is how many standard tents we're making, Y is how many expedition tents we're making. Okay, now if we plug in 0, 0, not surprisingly, our profit is 0. That makes sense, right? If we're not making anything and not selling anything, we don't have any profit. So obviously that's not going to be the ideal combination. Now another possibility is that we make 0 standard tents, but we spend all our resources on making expedition tents and we make 16 of them. So we have 50 times 0, so no profit from standard tents, but we have 80 times 16. So we make $80 per expedition tent and we're making 16 of them. That comes out to a total of $12.80. So if we made no standard tents but 16 upgraded tents, we have a profit of $1,280. Now another combination would be spend all our resources on standard tents but no resources on upgraded tents. So that would be 28 standard tents but no upgraded tents. So $50 per standard tent times the 28 tents we make, and then no profit from our upgraded tents. That would give us a total of $1,400. So notice so far that's going to be the best option. So far that gives us the highest amount of profit. Our last combination is some combination of the two. We're making some standard tents, we're making some expedition tents. That was that corner point in the middle of the region. That was where those two diagonal boundary lines intersected, so 20,6. So we're splitting our time between making standard tents and between making upgraded tents. So 20 standard tents, 6 upgraded tents. So $50 per 20, and then $80 for each of the 60 would give us a total of $1,480. Out of the 4 possibilities, that is going to be our best option. That's going to be the option that maximizes our profit. So what that tells us is the optimal solution, the combination that we want in terms of determining what our plan is, what we're going to make, how much time we're going to spend doing different things. The optimal combination is to make 20 standard tents and 6 expedition tents, and this combination will give us a maximum profit of $1,480. So we met the objective. The objective was to determine how many tents we should make of each type in order to maximize our profit, represented by this function, and it yields a maximum profit of $1,480. So that's just a taste of what this kind of problem is going to look like. Notice there's a lot of different layers. It can be less complicated, it can be more complicated. Ultimately, they all are very formulaic in the sense that we have the same kinds of things in every problem. We have an objective function that we're either attempting to maximize or minimize, and our objective function is dependent on decision variables. So those are the variables that we're trying to find the values for. Our decision variables ultimately are limited in terms of the values they can take on. So those values are, the limited values are determined based on our constraints. Those are our inequalities we write. So we have limited resources. We have to determine how are we going to allot those resources towards those different activities in order to maximize or minimize whatever our objective function is. So we write our objective function. We determine, do we want to maximize? Do we want to minimize? We need to determine what our variables are. Of course, that's going to factor into our objective function. And then we also have to write our constraints, which are going to be determined by what the limitations are on our resources per activity that we engage in. Okay, so once we have the problem written, each time we write it, it's going to look something like this. So this is going to be the structure of our actual problem. We have our objective function. We either want to maximize or minimize it, and it's subject to however many constraints we have. In this case, we had 2 problem constraints and then 2 non-negative constraints. We could have more problem constraints than that. Now we're just going to stick to 2 variables, which means max. We're going to have 2 non-negative constraints if we do in fact have those constraints. But we could have a bunch of problem constraints depending on the situation we're in. So every problem we do is going to look something like this. Either we'll be given a problem like this, or like we did here, we'll have to write the problem ourselves. So once we have the problem written, we know what our variables are, we know the objective function, we know our constraints. First step is to graph our feasible region. In other words, graph the system of inequalities represented by our constraints. Now from that feasible region, what we're looking for not only is where we shade, but what are the corner points. So determine where those different boundary lines intersect. The corner points are the possible locations, the combinations for X and Y that represent possible optimal solutions. So we're going to construct a corner point table like we did here, find all the corner points, organize them all into a table, and we're going to determine the value of the objective function with each of these combinations of our decision variables. The optimal solution is going to be whatever is optimal. So if our goal is to maximize something like it was in this example, we're looking for the location where we get the highest output for our objective function. If the goal is to minimize, say we're minimizing cost, something like that, then we're looking for the combination of values that would give us the lowest output. So our actual answer is going to have a couple different components. Not only is it going to have the optimal value, in other words, the maximum, the minimum, but we also need to know what combination of variable values, decision variable values, gave us that optimal number. Now, sometimes a problem like this doesn't actually have an optimal solution. We can create a problem that doesn't have an optimal solution, something we can't actually solve. We can find different values that work, but it may not be possible to find sort of the perfect situation, the optimal situation. So how do we know that we have a problem that can be optimized, where we can find a maximum, we can find a minimum? Okay, if our solution region, our feasible region, is bounded, in other words, we graph it and it's confined to a space that could be enclosed in a circle. This was a bounded solution region. We could draw a circle around it. It's bounded. It's enclosed within a polygon, essentially. Think of it that way. If our feasible region is bounded, then we can both maximize and we can minimize. So a true maximum and a true minimum of our objective function, they both exist. Okay, so if it's bounded, we can solve any problem we want and we're good. If the region is unbounded and the coefficients of our objective function are positive, so we're looking at our objective function, the coefficients, the constants in front of our decision variables are positive numbers. If that's the case, then we can find a minimum, so we can minimize something like cost, something like that. We can find a true minimum, but we cannot find a true maximum. Well, why does something like that happen? Well, if we graph a solution region that, for instance, say filled up the right-hand corner of that quadrant, notice that would be unbounded. It goes forever up and up and out to the right. That would be unbounded. Well, we can minimize because there are minimum values, there are lowest values, but in terms of maximizing, well, where's the maximum in a region like that? The answer is there is no maximum. For any number that we get that's big, we can find numbers that are bigger and bigger and bigger. So finding a true maximum when our solution region is unbounded isn't something we can actually do. So we can find a minimum, we can't find a maximum. Now it's possible when we write the problem constraints and we create that system of inequalities, it's possible that we can write constraints such that when we graph them, the solution region is actually empty. In other words, we could graph the individual inequalities, but there isn't actually anywhere where all of the graphs overlap. That's entirely possible. It can happen. If that does happen, in other words, there's no shaded region where everything overlaps, then there is no optimum value regardless. So we can't find a maximum and we can't find a minimum. So most of the problems we're going to do are going to be nice, well-constructed problems where we can truly maximize, we can truly minimize. But just keep in mind, if we're writing constraints based on a real-world situation, it's entirely possible that we may come up with something where there is no optimal solution. There are possible solutions, but there's no best case that we can find. So let's look at a couple more examples. We're not going to rewrite our own problem. We already did an example of that, but let's just look at some pre-written ones. Okay, so here's our goal. We want to both minimize and maximize. In other words, we want to do kind of two problems in one. We want to minimize and we want to maximize this objective function. So the function is z is equal to 3x plus y. So that means x and y are our decision variables. We're deciding what values those are going to take on so that we can get the maximum or the minimum value for this z represented as 3x plus y. Now our decision variables are subject to these three problem constraints and then our two non-negative constraints. So we know 2x plus y has to be less than or equal to 20, 10x plus y has to be greater than or equal to 36, and 2x plus 5y has to be greater than or equal to 36. Okay. So we need to start by graphing that system of inequalities. So I'm going to graph that system. Remember, graph the boundary lines. shade based on what side of the boundary line we want to keep based on our test point choice, whether the test point works, whether it doesn't. And again, focus on the corner points. So we're looking for the locations where those are going to intersect, where our boundary lines are going to intersect. And then again, our non-negative constraints just tell us we're going to stay within the first quadrant. So if I graph these three inequalities, this is going to be the region I come up with. Notice that region is already in the first quadrant, and it wouldn't go outside of the first quadrant anyway. So as it turns out, those non-negative constraints aren't actually going to matter in this case. So I highly recommend take a minute, pause the video, go and see if you can graph these. Make sure you can graph these and you get that solution region that we have right here. Now, if you put it on an actual graph, you may be counting by something other than ones. Notice I counted by twos here. That's fine, not a big deal. Make sure based on whatever scale you have though, you know where those corner points are. So our solution region, our feasible region is bounded. So it is a bounded region. As long as it's a bounded region, we know that yes, in fact, a minimum does exist, and yes, in fact, a true maximum does exist as well. The minimum and maximum are going to occur at one of the corner points. We can't look at it and immediately say, this is the combination that gives us a minimum, this is the combination that gives us a maximum. It's just going to depend on what those values do when we plug them into our objective function. So I'm going to take each of those combos from my corner points, plug them into the table, and then for each of the combinations of x and y, I want to evaluate that objective function at those particular values. So for 3, 6, if I plug it into my objective function, I get an output of 15. For 8, 4, if I plug it into my objective function, I get an output of 28. And then for 2, 16, my last corner point, if I plug it into my objective function, I get an output of 22. Okay, so as of right now, that's everything we need. We have to interpret what we're looking at though. So think back about the goal. The goal was to both minimize and maximize. So find the minimum and find the maximum. Well, it looks like our minimum is going to be a value of 15 for our objective function. So that's going to be the lowest we can get in this objective function based on the constraints we have for our decision variables. So the minimum of 15 occurs at 3, 6. So it occurs when x is 3 and when y is 6. Now the maximum we can get is going to be an output of 28. So the maximum value is going to be 28, and it occurs when we allow x to be 8 and we allow y to be 4. So that's the general idea. Notice how much faster that was. The longest part of the problem, hands down, is going to be graphing those linear inequalities, finding that solution region. The corner point table doesn't take all that long. Evaluating the objective function doesn't take all that long, and from there, it's just interpretation. Writing the actual linear programming problem can take a little bit of time. It takes a little bit of work. But once we have the actual problem structured, or say we have it structured for us ahead of time, it's fairly straightforward to actually solve. Okay, let's look at one more. Same directions. We want to minimize, we want to maximize. Now we have a new objective function, and we have some new problem constraints. So our objective function is going to be z is equal to 10x plus 20y, and it's subject to 3 problem constraints and 2 non-negative constraints. So the non-negative constraints again tell us our solution region is restricted to the first quadrant, and then x and y have to fit each of those inequalities. Now notice one of our inequalities doesn't have an x, it just has a y. If you think of the boundary line that represents, that's represented by a horizontal boundary line. So it's going to be a horizontal boundary line at 20. So that tells us 20 is our cap, vertically speaking. We can't go above y equals 20. Everything has to be less than or equal to that. So yes, we're confined to the first quadrant, but we're also confined to a smaller section of the first quadrant. So if we graph our other two linear inequalities, we're looking for where those intersect. We're also looking for the region to shade. We have, count them, 1, 2, 3, 4 corner points. And then we are restricted to the first quadrant. So where we would keep shading down here, we're restricted by the x-axis. The x-axis is our lower boundary. And we have 4 corner points defining that region. Now this is not a bounded region. Even though we have a boundary below and we have a boundary above, notice we don't have a boundary on the right. So all of this shading would continue towards the right forever and ever and ever. So this is a non-bounded region. What that means is that a minimum does exist. Our objective function has positive coefficients, so a minimum does exist, but a true maximum does not exist. For any combination of values we can find larger values and larger values and larger values. So z can get bigger and bigger and bigger and bigger indefinitely. So there is no true maximum in this case. So all we can do is minimize. So I'm going to take my corner points, put them into my table, and then I want to evaluate this objective function, z is equal to 10x plus 20y, at each of these combinations for x and y. So the combination 0, 18 gives me an output of 360. 0, 20 gives me an output of 400. So far the first one is lower. We're trying to minimize. Remember, we can't maximize. 16, 0 gives me a combination of 160. And then 4, 6 also gives me a combination of 160. So don't be fooled. 400 is not the maximum. It just happens to be the largest value that we came up with in this table. But remember, we could continue on forever and ever. Bigger x values, not bigger y's, but bigger x values. The bigger the x value gets, the bigger this function gets. So there is no true maximum. This just happens to be the highest value we got in the table. There is a true minimum though. So the true minimum value is 160. But notice two different combinations would give us that minimum value. That's okay. What that means is that there are in fact two different combinations that minimize our objective function. So the minimum value is 160. That's the smallest value that our objective function can take on. And that minimum is going to occur either at 16, 0, that's one possibility, or we could choose x is 4 and y is 6 and get the same minimum value. So either one of these combinations would optimize this situation where the goal was to minimize this function. Because this region is unbounded, because our x values increase indefinitely, even though there's a cap on the y values, the x values increase indefinitely, we know that there is no maximum value. So we can't find a maximum value of our objective function, and we can't find a location where we would in fact maximize.